Hello students, welcome back to session 7 of Hilbert spaces class. So in the last class we have studied what's meant by an operator on a Hilbert space, and you have studied normal operators and theorems based on those operators. Okay, now let us define what's meant by an unitary operator in this class, and projections on Hilbert spaces. We will study all these concepts in this class. Okay, suppose T is an operator on a Hilbert space H. Then this operator T is said to be unitary if T into T star is equal to I, that's equal to T star into T. So the operator T on a Hilbert space is said to be unitary operator. Okay, if T into T star is I, that's equal to T star into T. Now obviously unitary operators are normal because T into T star is I, that's equal to T star into T means what? T into T star is equal to T star into T. Therefore every unitary operators are normal operators. Okay, now let us take up few results on this unitary operators. So first one, suppose T is an operator on a Hilbert space H, then the following conditions are equivalent to one another. First one is T star into T is I, inner product of T of x comma T of y is inner product of x comma y for every xy belongs to H, and third one is inner product norm of T of x is same as norm of x for every x belongs to H. Okay, say first one, let us prove 1 implies 2. Okay, so we assume that suppose T star into T is equal to I. Now inner product of xy can be written as inner product of x comma y can be written as say this is equal to x means I of x is x because I is a identity operator, I of x comma y. I means T star into T of x comma y. Now I'll transform this T star to on the right, so it will become T. So T of x comma T of y for every xy belongs to H. Thus that's inner product of x comma y is inner product of T of x comma T of y, which is 2. Okay, so 1 implies 2. Now let us come to the 2 implies 3. Suppose inner product of T of x comma T of y is inner product of x comma y for every xy belongs to H. Now this holds for every y belongs to H means you can put y is equal to x, so that we get inner product of T of x comma T of x is equal to inner product of x comma x, that's equal to inner product of T of x comma T of x means norm of T of x whole square is equal to norm of x square. This implies norm of T of x is equal to norm of x for every x belongs to H, which is nothing but 3. Okay, 2 implies 3. Now let us take up 3 implies 1. Now, so suppose norm of T of x is equal to norm of x for every x belongs to H. This implies norm of T of x whole square is equal to norm of x square. This implies inner product of T of x comma T of x is inner product of x comma x. This implies inner product of T. Now you can transform this T onto the left, it becomes T star. T star of T of x comma x is equal to inner product of x comma x. This implies T star T of x, I'll transform the right hand side term to left hand side, it becomes T star T of x minus x comma x is equal to 0. This implies T star minus T star into T minus I of x comma x is 0 under inner product. So this implies what? So therefore T star into T minus I is equal to 0. T star into T minus I is equal to 0. This holds for every x belongs to H means this is a 0 operator. This is a 0 operator implies what? T star into T is I. Therefore, which is the required result, which is 1. Okay, so 3 implies 1. An operator T on a Hilbert space H is unitary if and only if T is an isometric isomorphism of H onto itself. The operator T on a Hilbert space is unitary operator if and only if T is an isometric isomorphism of H onto itself. First, suppose T is an unitary operator on H. Then by definition of a unitary operator, T into T star is I, that's equal to T star into T. This implies what? T star is nothing but T inverse. Okay. So if we transform this T2 on the right hand side, it becomes T star is equal to T inverse. So this implies T is invertible. Okay. T star is equal to T inverse, and T into T star is I means T into T inverse is I means T is invertible. So invertible means it is onto. Okay. This is T is onto. Now we consider the inner product of x comma y. So inner product of x comma y is equal to, so inner ix means I can write it as I of x comma y. I means T star into T of x comma y. So this is equal to inner product of T of x comma T of y. Now I'll substitute y is equal to x. In the above expression we get inner product of x comma x is equal to inner product of T of x comma T of x. So this implies what? Norm of x square is equal to norm of T of x square. This implies what? Norm of x is equal to norm of T of x for every x belongs to H. Now norm of T of x is equal to norm of x means what? T preserves isometry, T preserves norms, and so it is an isometry. So T preserves norms and an isometry. Already T is a linear transformation, T is a linear transformation, and now it is an T is an linear transformation. Now it is an isometry. Thus T is an isometric isomorphism of H onto itself. H onto itself. Okay. T is an isometric isomorphism of H onto itself. So we have assumed that T is unitary, and we have shown that T is an isometric isomorphism of H onto itself. Conversely, you assume that T is an isometric isomorphism of H onto itself. Now T is an onto itself means T is onto, and so T inverse exists. Also, T is an isometric isomorphism imply what? Norm of T of x is equal to norm of x for every x belongs to H. This implies norm of T of x whole square is equal to norm of x square. This implies inner product of T of x comma T of x is equal to inner product of x comma x. This implies you transform this T2 on the left, it becomes T star into T of x comma x is equal to inner product of x comma x. Now this implies inner product of T star into T minus I. So if we transform this to left, it becomes minus I of x comma x is equal to 0. This holds for every x belongs to H. This implies, so you know that inner product of T of x comma x is 0 means T itself is 0. Accordingly, T star into T minus I is equal to 0. This implies T star into T is equal to I. This implies T star is equal to what? T inverse. Therefore, T star is equal to T inverse means T into T star is what? T into T inverse is I. Again, T inverse into T is I. Therefore, T into T star is equal to I. That's equal to T star into T, which implies that T is a unitary operator. So we have assumed that T is an isometric isomorphism of H onto itself, and we have shown that T is unitary. Okay. So now note that if T is an operator on a Hilbert space, okay, if T is an operator on a Hilbert space such that norm of T of x is equal to norm of x, then what will happen? T is definitely an isometric isomorphism of H into itself. If T is an operator on a Hilbert space H such that norm of T of x is equal to norm of x, then definitely T is an isometric isomorphism of H into itself. But T need not be onto. Okay, T need not be onto means, so it need not be unitary. Okay, because for let T be an operator on L2, but T need not be onto, and so T need not be unitary. For let T be an operator on L2 defined by, so T of x1, x2, etc., xn and so on is equal to 0, x2 and so on. Then clearly what will happen? Norm of T of x is equal to norm of x for every x belongs to L2. Okay. Therefore, what will happen? Therefore, T is an isometric isomorphism. Therefore, T is an isometric isomorphism of L2 into itself. But T is not onto. Okay. Because if you take any vector, say any element of L2, say like y1, y2, etc., yn and so on, this is a sequence. Is a sequence in L2 such that first coordinate y1 is not 0, then there do not exist any sequence in L2 whose T image is y1, y2, etc. yn. y1, y2, etc. yn. Therefore, T is not onto and so T is not unitary. Okay, understand this? Therefore, T is not onto and so T is not unitary. Say next is, say suppose you know this definition. Let T be an operator on a Hilbert space H. Then a closed linear subspace M of a Hilbert space H is said to be invariant under T if T of M is contained in M. Okay, and closed linear subspace M of a Hilbert space H is said to be invariant under the transformation T if its image T of M itself is contained in M. Okay. Now, say this result says a closed linear subspace M of a Hilbert space H is invariant under operator T if and only if M per means orthogonal complement of M is invariant under T star. Okay, a closed linear subspace M of a Hilbert space H is invariant under an operator T if and only if M per B is invariant under T star. Okay, first let M be invariant under T. M be invariant under T means what? T of M is contained in M. Okay, now we need to show M per B is invariant under T star. For this, let X belongs to M and Y belongs to M per orthogonal complement of M be arbitrary elements. Then what will happen? Inner product of X comma Y is 0 because Y belongs to M per. Now, X belongs to M implies what? T of X belongs to M because M is invariant under T. T of M is contained in M. Therefore, T of X belongs to M. Now, T of X belongs to M means according to this, inner product of T of X comma Y is 0 for every X belongs to M. So, this implies inner product of X comma T star of Y is 0 for every X belongs to M. Now, inner product of X comma T star of Y is 0 means where T star of Y belongs to? T star of Y belongs to M perp. Thus, Y belongs to M perp implies T star of Y belongs to M perp implies what? M perp is invariant under T star. That is orthogonal complement of M is invariant under T star. Okay. So, we have assumed that M is invariant under T and we have shown that orthogonal complement of M is invariant under T star. So, conversely, suppose that M per orthogonal complement of M is invariant under T star. Now, look here. Since M perp is also if M is a closed linear subspace, then M perp is also a closed linear subspace of H, and which is, we have assumed that it is to be invariant under the operator T star. Therefore, now by the first part of the proof, because we have assumed that if M is invariant under T, then M perp is invariant under T star. Now, M perp is a closed linear subspace invariant under T star. Therefore, by the first part of the proof, M perp whole perp, that is M double perp, is invariant under T star whole star, that is T double star. So, T star whole star, that is T double star means, okay, T double star, that's called T double star is what? T. Now, M double perp is invariant under T, but M double perp is nothing but M. Okay, you know that. M double perp is equal to M, therefore, M is invariant under T. Okay, we have assumed that M perp is invariant under T star and we have shown that M is invariant under T. Okay, these are the few results for this class. Thank you.